Welcome back. As I mentioned in my introductory video for electronic configuration, that this is the view that I will be using, and I think you're welcome to use this because it's taken a lot of effort to put it in this way. So it's not only condensed, but it takes into account the periodic table rather than treating the periodic table as a whole separate component. Okay. Now, I have provided all the information that I spoke in the video as a shortcut note. You can see s orbitals contain 2, p contains 6, d contains 10, and f contains 14. Okay. Now, the electronic configuration we are going to learn right now is the free-flowing method, but we also would learn how to write the boxed method, and then finally the condensed electronic configuration. So there's different ways to approach the problem. This is my view. Now, I call it the orbital snake. I don't think that's what the textbooks call them. But you can see that these are the conventional methods you may find in your textbook. Now, what this is saying is this is not embedded on the periodic table. So that in itself can cause some visual confusion. But if you understood my view, you can understand this. If you want to follow this, that's fine. So what this is saying is you're starting with 1s, and then it goes like this to connect to 2s, and then connects it back to 2p, and then 3s, and then it connects. The line goes in between to connect. What students used to do is they connect the tail to an head, tail to an head, and then they see that, oh, that's not what my professor said, and they get it wrong. So this is how you connect. The connection happens between this, but to me, this is, again, I'm biased towards my view, but you're welcome to use your method. Now, this is another sequence, which is, I think this is really purely about memorization. So you're welcome to use that as well. But this is the method we're going to use, okay? So without further delay, let's focus on domain 1. Now, domain 1 is about row 1 through row 3. Why do I say that is because the rules for those are slightly different than the rules for row 4 and beyond, right? So we're trying to write the electronic configuration. Again, this is the free-flowing method. I call it free-flowing because it's not boxed, okay? We're trying to write the electronic configuration for magnesium, right? So to write an electronic configuration, you need the total electron count. How do we know the total electron count? That's what we learned in our previous material. You see, we're trying to connect the bridges, right? And if our atomic number is 12, how many electrons does magnesium have? You guessed it right. It's got 12 electrons. That means our total electron count is 12. Does that make sense? How we are relating the concept? All right, very good. Now let's actually get into the rules. Now this rule you can apply blindly following the sequence for any element from row 1 up to the end of row 3. Okay, there should be no exception to that rule. Okay, so first write the orbital sequence. So let me go back for now and see where our magnesium is. Well, magnesium is in row 3, right? Which means to get to this 3s band, I had to go through 1s band, which, I mean, the first row is only 1s. I had to go through, don't write 1s, 1s. What this really means is just 1s. There cannot be two 1s, okay? Can only be one of each of its kind, okay? You cannot repeat it. So 1s, 2s, 2p, and then I get to the 3s band, which is where my magnesium is. So what I do is, let me walk you back through the rule again. First, write the orbital sequence. Fill electrons in each orbital left to right. Keep in mind how many maximum an orbital can hold. And I have said, S can hold a maximum of 2. P can hold a maximum of 6. D can hold a maximum of 10. And F can hold a maximum of 14, right? And the final rule, make sure you don't overfill the last orbital in the sequence. Always make sure the electron count matches the atomic number. What do I mean by that? I'm going to actually show it to you. Okay, so first write the orbital sequence. Okay, Okay, so what I mean by that is, all right, magnesium is in the third band, right? I'm going to actually physically write it too here so that you can see. Well, I had to get through the 1s band, the 2s band, the 2p band, and then the 3s band, which is where magnesium is physically present. All right, so we write the orbital sequence. Fill electrons in each orbital left to right. Now there is something I didn't mention here, but that's what I meant by, I didn't explicitly mention it, but that's what I hear mentioned by you don't overfill. Okay, we'll focus on that term. So we have 12 electrons, right? S can hold a maximum of 2, so we can put 2. Never fill the last orbital until you fill everything else. Okay, don't always keep it like, put a placeholder on. So S can hold again 2. It doesn't matter which row the S is in, S can only hold 2. P can hold 6. Now stop. Why do I ask you to stop is this way you don't overfill. You want to make sure that as it is, the current count is not already past your total of 12. So we now have 10, right? Up till this point we have 10. So 12 minus 10 is, we only need 2 electrons, so we put 2. And if you see, now we have 12 and we have 12. Why do I ask this is because if you don't do this, I know I have seen students that always put the maximum irrespective of what the count is. Like for instance, P can only have 3 at that point if P happens to be the valence, but they just add 6 because they think, oh, because P can hold 6, I'm just going to add 6. Don't do that. All right. Always make sure the electron count matches the atomic number. Now count everything. 2 plus 2 plus 6 plus 2 is 12, which matches the atomic number of 12. Does that make sense? So that's what I've animated here. You see, I have wrote the band, filled it, stopped, and then I counted how much I need, and then I fill whatever's left. You see, it always works out perfectly. That's science. It's beautiful, isn't it? So let's say we try lithium. Okay, lithium is in, if you see, it's in row 2, isn't it? Right? And it's in the 2s band. So we have to first get through the 1s band. Don't write 1s, 1s. What I'm trying to say by that picture is both those elements in the first row have only 1s. Okay, 1s and then 2s. That's it. Now you start filling from left to right. And whenever you start from left to right, you can start filling the maximum. Just don't fill the last one. So this will be 2. Well, I have 3 electrons. Lithium's atomic number is 3, so I have 3 electrons total, right? I have filled 2, so it's 3 minus 2 is 1 is all I left with, and I can have 1. Now keep in mind, yes can have 1, it can have 2, but just not more than 2, which is why I ask you to stop, because what I have seen students, despite the rules, what they do is they fill 2 and then they say, oh yeah, he said yes can hold 2, so they put 2. Well, which could be a multiple choice option on the test. So I could give you 1s2, 2s2, and some people will go for it because they think, oh, he said s is 2, s is 2. No, this must match. So 2 plus 1 equals 3, 3, which matches the atomic number, right? So this is domain 1. That means the rules that I have here, I mean, the rule is really 1 and 2, okay? 3 is more of a caution, okay? That's not really a rule, but I tend to include it in the rule because it just makes sense. It's only first 2, A and B are really the rules. Third is more of a cautious warning, so that's, I guess you can call it a rule, right? So this is domain 1, which is row, any element in row 1 through row 3, they're part of your domain 1. So if you follow these rules, I don't see you should have any problem doing doing electronic configuration for any element in row 1 through 3. So I'm going to come back with another video for domain 2 and then explain the why and then do an example or two so you can see how it all works out. All right, so stay tuned.